Good morning. I want to continue talking about chapter 14 with you this morning. And now that we've gone through a variety of different kinds of sorts, I want to look at another kind of manipulation of lists that we might want to do, which is searching. And in particular, I want to look at the running time of searching so we understand the efficiency of doing those operations. So that when you do a search using any kind of programming language, but in this case, Java, you understand the kind of work that it's going to entail and why it might be slow. So for start, searching is just kind of straightforward. You may think of searching in terms of like the internet. That's a very drastically different kind of search with a lot more horsepower behind it. But when we're talking about search, we're going to just focus for today on looking through a list of elements in an array in order to find one that we care about. So generally, this could be anything, but let's just think about it in terms of a set of numbers. Let's say we have an array of 100 elements, and those 100 elements can have integers in them, and we want to search through that array to understand whether a particular integer that we care about is there. Maybe it's 17. One thing we can do, and the most straightforward thing that you can do, is called linear search. Sometimes this is also called sequential search. And both of these terms reflect the way in which we're going to go through the entire array step by step in a line or sequentially in order to find the element that we're looking for. This strategy involves examining all the values in the array until you find a match, find the thing that you're looking for, or until you get to the end and have to return some sort of signal that you didn't find what you were looking for. Now, in general, in order to know that something is not present, you're going to have to search through every single element of that array. You don't know that it's not there unless you look at every element. And if you assume that your array is n elements long, n being a variable that substitutes for the length of your array, then the running time in the worst case is going to be order n, because you're going to have to look at everything to know that it's not there. But generally, if we think on average, we're looking for elements in the array, no sorting involved. We're just looking through the elements in the array. Sometimes it'll be at the beginning, sometimes it'll be at the end, and you can say that on average, when you're searching for things that are present in the array, the running time is going to take about half the length of your array, so n over 2. Maximum visits will be n, minimum will be 1, and on average it's n over 2. So when we determine what the efficiency of that algorithm is, we look at what is the highest order term in our running time, that's n over 2 because that's all we've got, and we throw away any constants, in this case 1/2, leaving just an order n algorithm. And again, what that means is that as the length of your array grows, the amount of time that it takes to search your array grows, and it grows in the same amount. So if you double the size of your array, it's going to take twice as much time to search that array as it did before. So it's kind of a straightforward algorithm. It's a straightforward analysis. And what we can do is we can look at some code that sort of just demonstrates and makes concrete what we're talking about. So let's see if we can do that. So this is an example of code, a linear search code. And as we look at this, we see that there is just a class that has one function. It's a static function. So that means that the static function has no access to instance variables. And what we're going to do is we're going to search through an array that is passed in as a parameter, and we'll call that array A. That's what we're looking through. And then the element that we're looking for is going to be value. And so the search method does the work of looking through the array to try and find the element that we're looking for. Does it with a straightforward while loop. Line 16 there, it starts at the beginning of the array, it goes to the end of the array, and at each element, it checks to see whether the current element, A bracket I, is equal to the element that you're looking for, value. And if it is, then we return the index that we found it at so that the user who called our function can find it themselves if they want. And if we get through that entire array, if we go through all of the loop in line 16 and we don't find what we're looking for, then we return -1. And in this case, -1 is a signal that we didn't find what we're looking for. All right, so you have to think a little bit about the design there, because what that implies is that there isn't a -1 in your array. So there's a little bit of like design decisions about how you indicate that something's not present. So for the purposes of this example, we're going to assume that our array only contains positive integers. All right, so how might you call this? This is the library function. How does a user who wants to use this function call it? Here's an example of a demo. This is a separate class that has a main function, and this main function will call that linear searcher. You can see on line 11, we actually set up the problem that we're interested in. This is going to leverage a helper function that we have in a third class that I'm not going to show you. The third class is arrayUtil. That has a method that we wrote that's going to fill an array of 20 elements with numbers between 0 and 99. I think it's 0 and 99, maybe 1 and 100. We're going to print that out, and you can see that in the program run, line 12 executes right here. You can see that showing up right there. That's the result of running line 12. And then we ask the user for some input on line 13, or we create a scanner on line 13. We create a sentinel on line 15, and we continue asking the user for input until that sentinel is false, or till done is true. So on line 18, we ask the user what we're going to search for, and in this case, we'll use -1 both to indicate that something hasn't been found and for the user to enter it in to quit doing the search. In this case, they looked for the element 12. It was not found, and so we returned a -1. We had to look through that entire array in order to do that, and then when we came back to line 18 and the second time through the loop, the user entered -1, and then we quit the demo. So linear search, a pretty straightforward example of searching through an array with a running time of order n.